Okay, everybody. Welcome to the 7th installation of our machine learning seminar at HZG. Today, it's going to be presented by me because David is out for this time. He'll be joining us again for the next session. So the topic for today's session is, as we wrote in our email to the group, the paper Latent Space Physics towards learning the temporal evolution of fluid flow. Since today I'm hosting the session alone, I'm encouraging everybody to chime in with any questions, not even raise your hand, just unmute your microphones and raise a question if you have, just to avoid me presenting a 1-hour monologue on stuff, and to maybe get a bit more of a discussion going on this. So the idea is that we go through the main paper first, this Latent Space Physics paper, discuss what they're trying to achieve, discuss where there's still work to be done. Then we're going to quickly glance over the underlying concepts for machine learning. This will be autoencoders and sequence-to-sequence models in this case, which are the building blocks for the algorithm that we will be looking at today in the main paper. And then there will be two follow-up papers, or one direct follow-up paper, latent space subdivisions, and then a very related paper that we'll very quickly touch upon. Maybe I just even show parts of this video here, that also is from the same group and goes in the same direction. Yes, and as I said, we will also have a quick look at the autoencoders and the sequence-to-sequence models that are relevant for all of this. But yeah, let's look at the task, at the topic of this seminar. So the idea is to learn the dynamics of some physical system, in this case a fluid, described by Navier-Stokes like equations. And the task is to learn from a short input segment of frames, as we can see here in this summary figure at the left, how to then continue the video of 3D volumetric images into the future. And why is this interesting? Why is this relevant? Well, it has been solved. So the original training data also for this method comes from viable numerical solvers for the problem that can, at acceptable resolution and in particular at high fidelity, simulate these systems under the given initial state and the border conditions. So why would you like to do this now with a machine learning with a machine learning model? Well, the main thing that is put forward also by the authors is that it might be faster. We might be able to train a deep learning architecture that takes in a sequence of images and processes them and returns a sequence of images that is running faster than the numerical solver. Another interesting aspect of this is more from the scientific side, is whether at all this is possible. We will see here that it has to do, as you can already see here in this overview image, it has to do with some sort of compression of the individual images. Here shown by these function boxes, FE, which is the encoder network or the encoder function that is applied to each of these volume images individually. And so the question is whether or not you can even learn meaningful compressed representations of these system states that capture everything that's relevant to predict their future states. So there's also a scientific aspect, whether or not it's possible at all. Now, from the basic setup of a machine learning approach to trying and learning how to, emulate these numerical solvers, things don't look so bad. So we have these numerical solvers, so we can, given enough computational power, produce our training data sets at will. We will later see in the main paper that there's even a few nice tricks you can use to augment your data to generate, to get more training data out of your simulations than you really need to invest in raw computational time. And as we will also see, there are network architectures based on convolutional networks and on LSTMs, both of which we've seen in previous seminars, that kind of suggest themselves to be tried out in this context. For the earth science experts among us, it might be interesting to see what are the first steps in this direction. But to look at this paper already in mind with questions regarding, is the Navier-Stokes formulation that they're using, is it really capturing everything that we want, or is it oversimplifying at certain points? And the other question, of course, being this here, as we see also in this top left picture again, is about fairly local systems that are simulated over short stretches of time. So how could we imagine this scaling up to the systems that we've also looked at it in previous seminars already? Okay, so if there are immediate questions, just for clarifications or just interesting points that came to your mind right away when looking at the paper, the main paper for today, we can also do this now. Otherwise, I would be starting going into the autoencoder and sequence-to-sequence machine learning concepts. Okay, if there's nothing from the side here of the audience in the Zoom meeting, I would quickly delve into a blog post on autoencoders, how they're used, what they do, and already maybe get an idea for how they might be very relevant here in this setup. So I don't know how many of you have clicked on the link and read through the blog post after I sent it around with the email. So an autoencoder is a structure for a neural network that essentially contains two different networks, and the task is to take an input of a multivariate signal. Here in this case, you see an image with 6 input nodes, so this would be a 6 pixel or 6 voxel image if you want, that gets passed through a network. Here's a very simplified sketch of that, and that has the same number of output layers, and the output layer activation is supposed to reconstruct what's going in. And why do you do this if you have the input already? The idea is that you push this through some sort of bottleneck, as it is in the middle here, that enforces the network as it tries to reconstruct the output from the input to learn some sort of lower dimensional representation. So in a slightly more detailed look, what this does is it has an encoder network, which is shown here on the left side, which takes the input, which may have a bunch of its own layers and activation units. We will see in the main paper of today, I think it's 17 layers for the encoder network and 17 for the decoder network. No matter how many intermediate layers, there's usually one, at least at runtime, one specific layer that is considered the bottleneck and whose activations are then often called the latent state. of the network, even though if you look at this graphic, in principle, any of these layers could be called some latent state. But the point is that there is one hidden activation layer that we consider the bottleneck, that is usually the one with the lowest dimensionality and hence the highest compression rate. And the idea is to interpret this as some sort of, again, latent representation that after training can be used either to store all the relevant information of an encoded data point or to decode the full image again from this summarized lower dimensional state. Now, if you look at the original structure in the simplified autoencoder, depending on which of these weights of this very simple, well, if you want, two-layer network, which values you set for these weights, these kind of autoencoder actually comprises a very simple case that we might all know from other work, which is a principal component analysis. So if the weights that go into each of these nodes consist of the principal component vectors that we get from a PCA, and if we additionally impose some constraints on the activity here, like orthogonality of the weights, then we actually get PCA as a special case of an autoencoder. But of course, the idea of the autoencoder being that you can make the individual steps much more complex and much more expressive, and as we see in this particular figure here, non-linear. So this is a nice little sketch to see why an autoencoder might be doing better than a PCA, which is a perfectly linear model. So here in this case, we would have two input variables on these two axes. So this would be x1 and x2, and there would be no further input dimensions. And you would have a single hidden node. So for PCA, that single hidden node would just be the activity of the first principal component, which if you did that, what it does is it tries to find the axis along the data set, which would be these blue dots, each individual blue dot being a point in this two-dimensional input space. So what it does, it tries to figure out the direction of maximal variance in the data set. And then what it would do in order to encode each of these data points is it would project, for instance, this data point onto this axis, and then the position along this axis would be the decoded point, the encoded information for this point. And then the decoder would then put this back from just along this axis, which you could think of for now as this being like 0 and this being 1 on this axis. It puts it back into this 2D reference frame. So the reconstruction, say, for this point of a PCA would then be something along this line. Now an autoencoder is a nonlinear method, so it still has a one-dimensional latent state in this case, but because the encoder and the decoder networks can both be nonlinear, where this one-dimensional state lies, in this case in this two-dimensional ambient space, is no longer just a line. So what this would do is it would take all of these points in these data sets, it would learn the transformation of these data points that gives you this curved green line from data, and then it would reconstruct these data points first by projecting each of these data points onto the green line instead of the red line, and then from this compressed state it would then also project it back into the 2D reference frame onto the point of the line that is closest to the original data point. As that's somewhat understandable, does anybody have questions regarding the concept? and the comparison to linear methods such as PCA. This is the very basic idea that you can have a nonlinear encoder into a lower dimensional space and then a nonlinear decoder from that nonlinear space. There's different variants. This is a very nice example from 3D to 2D, where you have 3D points in this kind of benchmark problem from machine learning, which is the Swiss roll. They're color-coded so that you can see all the points in 3D, but these are all just individual data points. In 3D, you just learn from a method that even though all of these data points are in 3D, there's actually a two-dimensional manifold if you unroll the Swiss roll. And then what the algorithm can learn is to take each point from 3D and map it onto a two-dimensional representation. And then it would learn how this 2D manifold here lies within the 3D space, so it can take this point back and do a very, very good reconstruction in this case. How good these reconstructions work depends on how high dimensional the input space is. Relative to that, how low dimensional is the bottleneck space, and also, of course, how is the structure of the data within the input space? Does it lie close to something that is on a lower dimensional manifold as here? So one thing that we will touch upon very briefly in the follow-up paper, not the main paper of today, is the idea that you do not necessarily need to impose the constraint of the bottleneck in this central hidden layer just through the number of units that you put in there, so the dimensionality of that hidden state vector. But you can just also control it through just how many of these you're allowing to be active at the same time. And then some other cool stuff that might be interesting for a future seminar, but not for today, is that these can also be used to denoise inputs. So if you feed a noisy input of your original images, the decoder, the autoencoder can learn not to just reconstruct it, but to at the same time to also denoise the data. And something that is touched upon at the bottom of the blog post here that is not entirely relevant for the main paper today, but which does a bit point to a big field with autoencoders is what is the structure of the latent space? So the activity of these hidden units that results from feeding some observed image or some other input data into the network. If I give two different inputs, if they're very similar, will actually be the hidden state activation also be similar? Or can it be something completely different and the network just learns something very non-smooth that just happens to work to explain the data, but behaves very unintuitively? We will later see that this is particularly relevant in today's main paper because they train the autoencoder, as we will later see. They train the autoencoder part before they train the temporal prediction part. So one of the things that might really bite them is that the autoencoder part can put the latent states for images in consecutive pictures very far apart from each other. That's something that actually the follow-up paper tries to address. Okay. So this is for the autoencoder part, so FE and FD in this picture, where the encoder encodes a high-dimensional input data point into some low-dimensional vector, and then this part we'll talk about in a second. You have the decoder part, which takes a low-dimensional vector and tries to reconstruct the high-dimensional image in the input space. Okay, now talking about this part here, which, as you can see, goes from time point t to t+1, so it does some temporal integration and some forwarding. That's sequence-to-sequence modeling. It's cited in the main paper, though not very prominently. So sequence-to-sequence is a framework that comes originally from natural language processing. The original paper, I have it open. Sorry for this. No, no, I don't. The original paper is somewhat not helpful to look at as right now. I mostly included it for historical context for those that are interested. So the context of that was that people had really some trouble working with sequences in natural language processing where the input sequence didn't have the same length as the output sequence. So if you remember what an RNN does is, let's look at the right side of this figure. So an RNN takes in a sequence of inputs, these red blocks at the bottom, and then it produces a sequence of states, each which depend on the previous state, so the block to the left, and on its input. And then it can produce a sequence of outputs correspondingly. So one thing that people noticed quite early on in natural language processing, that if you do this with sentences of natural language, in this case ABC being an input sentence, and W, X, Y, Z an output sequence, that this very, very simple viewpoint here doesn't do it. So one thing that sequence to sequence came up with, and that's the core idea of this, is that instead of having a single recurrent network that does everything in one go, you split it up into two parts. A first one, which is essentially a many-to-one RNN. So what this one does is it takes in a sequence of inputs, it produces a sequence of states that each depend again on the previous state and on its input, and then it produces a single output that is read out, and it is storing the entire information as a squeezed summary representation of the full input sequence in this particular state. And now if you combine this particular state then with a one-to-many RNN, which just produces outputs from the evolution of its internal states, if you combine these two things, you can get these sequence-to-sequence type structures, which have a first part, which is again called an encoder, and then it has a second part, which is then usually called a decoder. So here everything is drawn as one continuous line. In practice, it's usually two different neural networks. In the original publication from 2014, sequence-to-sequence learning, I don't think it actually was an LSTM, but in our main paper today and in most applications, these are these gated versions that are just nicer to work with in practice, and I think we've encountered this 3 or 4 seminars ago. So with these two basic things out of the way, autoencoders and sequence-to-sequence models, I'm asking again if anybody has any questions, any remarks, anything they found interesting when looking at the source material. Otherwise, I would be going to the main paper. So there's a question from Eduardo: are autoencoders in general easy to train in a standard case? So the thing with autoencoders is that it's a big thing of the structure for the network that you're using, or the two networks, if you will. If you go back to the easiest case of an autoencoder, if you've ever run a principal component analysis on any programming environment, you've trained an autoencoder in some sense. I think you can even write down a loss that you optimize iteratively the way these neural network weights are set, that gives you the same solution as does a PCA, which usually works with a eigen decomposition of some covariance matrices. So if your encoder and decoder networks are very simple, then yes, it's super simple. If these things are more complicated, then as we will see in the paper in a moment, there are tricks to getting it to run. The main problem that the literature has focused on in recent years isn't so much getting these autoencoders to reconstruct the data at all. If you make these layers deep enough and you use these encoder and decoder networks deep enough, and you use enough tricks, you will eventually get something. Just throw enough parameters at it, I guess. The main question that people were asking is like, how useful is the latent representation? Like, ideally, can we interpret it? Can we interpret some of the variables as something semantic that we know about the data? So we will see in one of the papers they're trying to split this by its content to contain something about the simulation setup. In principle, if we train an autoencoder and faces, one of the variables can be the age and so on and so forth of the person. So this is the trickier part to get to do, but training autoencoders is essentially training a feed-forward neural network with squared error, which is one of the most basic cases of deep learning to do. It's just that you have fewer. It's just that you have fewer units in some layers, which you wouldn't do with a pure feed-forward network. Okay, sorry, there's another question from Maria. What is the structure of the data that the autoencoder can handle? Can it be used in 2D data where the first dimension has much less data points compared to the second dimension? So if I understand the question correctly, I can actually bring... If this is okay with everybody, I would bring the Zoom chat into the picture that also gets put on YouTube. I'm going to wait for a second if anybody has objections. So if I understand correctly, the question regarding data being, for instance, 2D, with the first dimension having much less data points compared to the second dimension, being on an individual data point. Is that correct? Here we have a 2D example, right? We have two axes. Well, if you say I have 2D input data, which is an image of, say, 20 by 100 pixels, it depends on the structure of the autoencoder, the encoder and the decoder that you want to use. But naively, if you have 20 by 100, or let's make it even more extreme, 2 by 100 images, whatever those might represent, these are just 200 numbers, right? These are just input layer x1 until x200. Now you could train this then again with a fully connected network that encodes this into the hidden state. It just takes 200 input numbers and it just has a lot of weights. So from a parametrization perspective of the network, that doesn't make much sense. Now, with image data that is very, very balanced in terms of the dimensions of the two input dimensions, right? If it's an image, say 40 by 40, you would definitely use a 2D convolutional network for that if it has image structure. If it's very unbalanced, like 2D by 100, you might go with a 1D convolution, which is also used at some point in the paper as part of the decoder. So it's a question then of designing the encoder and the decoder to handle that structure. But in many cases, this again is just a question of hitting the literature on what kind of networks there are. And there's a ton of networks eating a ton of different data structures these days, from images to sequences to computational graphs, like in graph theory graphs, sets, all kinds of things. Geometric deep learning is pretty cool in an active field. So did that answer the questions? And are there any more? Otherwise, I would go to the main paper and delve in a bit more deeply. Where is my main paper? This one, I think. Okay, sorry. Should just go to the top. Okay, so onto the main paper. We've already seen this picture telling us the main setup. So we have these high-resolution volumetric images. I think in this case here, they are 128 by 128 by 128 cubes. And what we see here is a rendering, so a projection onto a certain observation plane. But what the networks really get is these 128 by 128 by 128, which is a lot of data. That's where is that? Almost 2 million data points per time point. Then you have a sequence of those, and then you want to predict either a single future state that would result from a numerical solver that goes from the final state a few steps into the future, or you want to predict the whole sequence of those. So the idea here was to use the two building blocks that we just introduced, an autoencoder to first do compression into a lower dimensional latent state, and then a sequence-to-sequence model to learn the temporal prediction in this reduced state. So the sequence-to-sequence model would get a sequence of these lower dimensional states. I think they're using 1024 up to 8,000 dimensional latent states. These are then just vectors without any spatial structure like images have. And then predict in this lower dimensional space and then decode back the images. Okay. So there's a bunch of equations. I'm not sure if they've been optimally presented for pedagogical reasons. Here's something that I alluded to when I was answering Eduardo's question from before. How are they trained? How are these autoencoders trained? So in this paper, they start out the process by first training the autoencoder network. So it's getting the input volumetric images, and it's supposed to produce the output. And these are deep encoder and decoder networks, each with multiple layers of 3D convolutions, having in total dozens of millions of parameters. One trick that they're using in this paper to get this to work is something that's called greedy layer-wise pre-training. So instead of starting with all of the layers, I think they have in total 17, what they start is with a first layer of both the encoder and the decoder, and they just train this shallow version, which is much less parameters. And then based on that, they stack and add more and more just to guide it, the parameters during training to start out from, when they add deeper layers, to start out from something that produces anything sensible. And then at the end of training, they go through the full encoder network into the latent representation, and from that back to the full decoder network. That's one of these tricks that you can do to train autoencoders. And that is utilized here. I must be honest, I haven't seen this in recent years. It's cool that they're using this here, actually. Okay, so as you can see, these are the dimensions. So the encoder and decoder networks, they're convolutional. So there's a number of channels which you can choose. And there's an image size. So the input goes in with a certain size R and the number of features, where D is either 1 if they're predicting the pressure fields, or 3 if they're predicting the velocities. So these are each 128 by 128 by 128 cubes, and at each of these grid points on these cubes, you either have 1 number or 3 numbers. So in a convolutional network, you'd call these features or channels. What each of these encoder and decoder layers does is essentially halves the resolution, and it doubles the number of these features. By the end of the day, you have something that sees for a 64 by 64 by 64 cube, the whole cube, and through the lens of 1024 latent dimensions, and then the decoder grabs these and it goes back into the observed space. Now, regarding the LSTM, what the LSTM does, so the temporal predictor, it takes in these, for every time point, these 1024 dimensional, I'm sorry that this didn't work out, these 1024 dimensional latent representations, here denoted by C t, the t-1 until t-n, where n is the sequence length. For each of them, it passes them into an LSTM unit that produces a hidden output, and that feeds back for t-1, t-n into itself. So you get this, I quickly made. So you get this structure of looking into the past. The structure of looking into the past and looking into its input. And then comes out this one representation, D, that is supposed to encode the entire video. They copy that, which is a bit confusing at first, but what it means is that each of these states of the future output is informed by the same D. So not only this state, as in this figure, would get the latent representation, but also the follow-up states. Let me quickly do another figure, just to confuse you. Ultimately, so you have an encoder. So don't look at the variable names. This is from a different paper, so every name changed. So our D here, our D from before is the C here. But what happens is you have a sequence of input images that gets read in by the input recurrent neural network. It produces the state. I could show this. It produces the state D, and this D then gets repeated and fed into all of these states for the decoder network. So this kind of spreading of information. Just because I personally stumbled over this figure. Somebody tell me if I'm being too explicit here. And now one trick that they do here on top of that is that instead of having a usual multilayer LSTM, So one thing that is often done with an LSTM is that an individual LSTM is like a single layer of a neural network, right? What it does is, at heart, it takes its input, D, and it applies a linear transformation to it, a matrix vector product, and then it applies a nonlinearity, and that's it. An LSTM has multiple compartments, it has multiple gates that each interact on the input, but it's still just 4 linear, nonlinear functions, where linear just means matrix vector, and nonlinear then usually just is something very simple, like a pointwise tanh function or sigmoid. So in order to gain more expressivity, to do something that is more nonlinear, what you do is you stack several of these. Now the problem with each of these modules, if I can scroll down, I can also just remind you of the equations of an LSTM. So these are the different gates of the LSTM. As I said, these are these simple functions, sigmoids and tanh, and then you have these linear functions. So some parameters times your input, right? Now these parameters, if your input is 1024, then these parameters will usually be 1024 squared. When they go to very high resolution images, they increase the latent dimensionality from 1024 to 8000, and then you would have an 8000 by 8000 matrix here, or maybe here, sorry, for the hidden states. And you will have that 4 times in each of the LSTM layers. So if you stack 2 for expressivity, you end up with 8 of these matrices. Again, you have actually individual matrices both for the last sequence input this way and this way. So a lot of parameters. One way to avoid this full matrix vector product is to do a 1D convolution along the axis of the vector. So if you imagine, for lack of a better example, I'm going to go back to just this part of this image. If you imagine your input as being a lot of numbers in a high dimensional vector, 1024 or 8000 as you like, instead of connecting everything to everything, what you would do is you would define a convolutional kernel of size, I don't know, maybe just 3 elements that takes an inner product with itself on the first 3 elements, and then itself on the next 3 elements, and then itself on the next 3 elements. So you, in this very, very simplified case, you would only have to specify 3 elements of a convolutional kernel that you convolve this one-dimensional, 1024-dimensional vector with just one axis with, which is much fewer parameters than the full vector matrix product of the LSTM. So this they do in order to save parameters, and they say this allows them to add another layer of nonlinear computation onto the LSTM without blowing up their the GPU memory. Okay, so this was pretty much everything from the machine learning setup that goes into this. The rest would be data and results. So if anybody has a question, now would be the time. I'm gonna start already talking a bit about data, but feel free to ask on the chat. So what is this actually being applied to? There is a bit of a cool idea regarding treating dynamic and static parts of some of the fields that we're trying to work with that you can read up. It's actually quite nice, but what this is applied to is, as I said, these cubes, these volumetric cubes of data that have different parts to it. There is a There's a velocity, so at every point in this 64 by 64 by 64 cube. There's 3 numbers here color-coded that show you where things move. And then there's another number here split into the static and the dynamic parts that gives you where the current pressure is. And now we're usually looking at these renderings that to the human eye is easier to understand. But what the algorithm has to do is it has to take a state that consists of both pressure and velocity, and it has to produce the next state of pressure and velocity that is correct to that degree that if we do a rendering of the future state, it looks nice, pleasing, and in particular it looks sensible, like a continuation of the motion that we saw in the previous parts. With this paper and the results done, I'm sorry. Let's have a quick look first at the data set that they're generating. So as I said in the beginning, what is nice about the setup from a machine learning perspective, and which makes this very interesting to look at, is that data is generated through simulation. So it's not a natural observation process, it's not an experiment that has to be done under very, very tough to replicate conditions. It's just a computer simulation. Okay, getting those to run under replicable conditions may also be not so easy, but it's a computer simulation, so in principle the amount of data you can generate is simply limited by the amount of computational power that you're willing and able to invest, which is a lot these days. I think even if you later have a look at the hardware they use for this study, it's not that particular expensive. I think they used a graphics card from 2014 for the neural network training, and the CPU, I wouldn't be so sure, but it seemingly wasn't the full cluster. So what they do is they generate scenes, so these are the different resolutions. They have 2 liquid data sets that we saw before, and then they also have a smoke data set, so for smoke plumes, sorry. And for each of those, they generate a certain number of scenes. So a scene is defined by an initial state. Let's see if this is pretty much where I wanted to end up. So these are initial states, and then so the renderings of those. And then what happens is that, well, gravity kicks in, and then these objects, these fluid masses, they move, they splash down, and things start to mix up and get interesting. So they generate several thousands of these scenes. They discard a few of the initial vectors, and then they focus on the dynamics part. They use length 100 sequences for training. And then what they do is they predict, sorry for all the scrolling, they predict given future states. Okay, where were we? One thing that is interesting to note is just the size reduction from going to these volumetric 128 by 128 by 128 cubes of both pressure and velocity down to these few thousand dimensional latent states from the autoencoder. Okay, so how do they train? How do they evaluate? So evaluation is done with this, to me, somewhat unknown distance function. What goes in is the surfaces, the surface representations, and then it essentially sums over a mismatch over every point of the surface. What is a bit curious to me is this 1 over and how it might behave. Because it's a max, and how this loss behaves, I must honestly admit at this point I have no no personal experience with this. But this is one of the error metrics that they use. So for this prediction surface error, we want to be as low as possible. And then there's another one, which is the peak signal to noise ratio, which we want to be as high as possible. There's something on the dimensionality reduction and on the architectures that you can read up on that I will glance over now. So for evaluation, the first thing they look at is the first thing they train, and that's the autoencoder. So here we have a still image rendering of a single frame, and then we have a bunch of other renderings that come from states of the system that have been partially autoencoded. So some of the variables were encoded with the autoencoder and then recovered from the autoencoder from the bottleneck low-dimensional representation, and then they were rendered again. Now, why is it interesting to look at these things? Because we expect that the compression that goes with the autoencoder will not contain perfectly all of the information that is going on in this dynamic volume. Now, there's a lot of information if you look at these, just intuitively at these masses of fluid, that can probably be compressed, like everything that's below the surface, that's just below the surface. There might be movements within there, but you might be able to represent that for a bunch of pixels in a local neighborhood. But generally, a perfect reduction of the information of the full system size by a factor of 2 to 300, as they have it, will be difficult. So there's going to be reconstruction loss. So what they try out is they take several of the variables and they auto-encode them, and then they see what comes out. As you can see, if they do the pressure, the autoencoder on the pressure, it generally captures the overall structure of the scenes and keeps that. Sorry, it doesn't capture it. Keeps that overall structure of the scenes pretty well. As they note, there's some high frequency stuff that gets sometimes added by the network for the network encoding the pressure. If the network's supposed to encode the velocity fields, things start getting a bit more distinct from what's supposed to come out. So one thing that has to be said about the whole approach here and the differences between encoding and decoding different parts of the network, as I understood it, is that the autoencoder network only replaces a small part of the simulator. So this isn't the full replacement of the numerical solver with the autoencoder. Especially if you only autoencode the pressure maps, the pressure fields, the velocities are actually still computed from the pressure fields using a numerical method. So this may be one of the big factors, as I understand it at least, of why some of this turns out much better than the other. From our perspective, what hasn't been, I think, very clearly communicated, at least for large parts of the paper, is that this doesn't necessarily replace the full numerical simulation, and it doesn't also have to, if the main point is a speed up or understanding what is possible and what isn't. So the computation of the pressure, at least that's what the authors claim in the appendix, is taking a good chunk of the full runtime of the numerical solver, so that even if you just partially replace it, you can still be faster by, I think, at least an order of magnitude. Okay. So these are a bunch of graphs that are somewhat overwhelming at the beginning. I just want to focus on on a very few things. So these are surface distances. So this is the error we want to be as low as possible over different prediction time steps, as you can expect. The further into the future we predict, the worse we get. So here's the thing that they mentioned, that if you actually encode the velocities, and hence your simulator takes over the full function of the numerical solver, things usually turn out a lot worse than if you just encode the pressure. Another thing that they say is like, look, we're essentially having a method that replaces for a certain amount of time a numerical solver. That doesn't mean we have to use it all the time. So one interesting idea that they have is that they intermit, and that's the C figure, the panel C that I want to look at, is they intermit the full numerical solver with steps that have the network take over parts of the numerical solver. And as you can see, depending on how you do this, how often you do this, you can actually massively improve the truthfulness of the prediction at a cost that is going to be proportional to how often you use your numerical solver and not substitute it. There's a bit of a technical detail that I wasn't quite sure if I followed it regarding where these computations are done. So on the network, in most frameworks, is handled on the GPU, whereas they explicitly compare to a numerical solver that lives on the CPU. So there might be some overhead of switching back and forth that might be hard to deal with. I can't say much on that. But the idea of replacing only parts of the simulation that are very of the numerical solver that are very costly, and the idea that you don't have to fully replace it in order to get out something that is sensible, I think are really worth stressing here. Does anybody have any other question or any other point about this results graph, this results figure, something they struggled with, that you want me to talk about? Just raise your hand or just chime in. Otherwise, I'm going to go to, I think, one of the most intuitive and I think also most conveying pictures of the study. So here they have a 2D setup. So instead of X, Y, and Z, they only have the depth, so the axis along which gravitation works, and then a single axis perpendicular to that instead of two. And what you can see is the round truth simulation evolving from something that has this single peak in the center to something that over the course of several frames develops two smaller peaks. And then you can see that with their combined method, if you run purely the predictive network, so IP equals infinity, is their way of letting us know that they use the network not intermittent with the solver, then you can see that the general gist of what's happening is actually pretty well caught. You see the single peak, and there's a bit of noise on that because of the autoencoder not fully recovering its input. So you see the peak does indeed split into several ones. What you do see, which they also discuss here, is that the autoencoder already introduces a bunch of noise on the fine details. But the interesting thing to me from these figures is that the LSDM then doesn't really degrade the result that much. So it seems to be more an issue of actually compressing the information in this very, very high-dimensional volumetric image than a problem other than doing temporal predictions in that space, which is interesting because these dynamics are kind of complicated. They're happening at a very fine scale everywhere at the same time, right? Okay, so then let's maybe just talk about this one here as kind of the pretty example. So here they go to the high resolution and they show us what the quality, just the image quality of the output looks like for individual predictions. First for the water data set and then for the aforementioned smoke data set. Here they make a point that this is actually tested, so these things went in the training data set. So there is generalization, and so they can form these very peculiar shapes out of the fluid before starting it when it then drops down, and you see the results evolving. So what you can see is that given that it is, as I understand it, largely the outcome of a neural network decoding a 1024-dimensional vector, that this comes out as something that looks like a somewhat realistic snapshot, especially this one here, the t equals 200 mark. I found quite nice. I must admit that there seems to be, as I said before, there seems to be components of the numerical simulator that are still used for predicting these images that I must admit I haven't fully parsed in all of their detail, partially because I personally not very familiar with the numerical solver methods yet. So if anybody wants to have a comment, somebody that read the appendix on what they call the flip method and how it feeds back into the network prediction, I'm very happy if you want to comment on how much you think the beauty of these results or the visual appeal of these results actually comes from some sort of post-processing on the network output that I'm not fully understanding at this point. Yeah, please chime in if you feel like it. Similarly, here's a smoke example. So what they have in this case is they have different sources of smoke that they place randomly into the image, and then they just let the dynamics run. And as you can see, even across large time skips, when a lot of stuff has happened, what comes out seems like a smoke plume. It seems consistent. It seems, at least to me, somewhat realistic. But I haven't really personally worked with these kind of numerical simulators. Yeah, so with this, I would, slightly above the 1 hour mark, I would conclude the main paper for today with just having the author's notes on the limitations in the back. So what we've seen is a paper that combines different blocks of architectures from deep learning into one algorithm that isn't trained end-to-end in this case. We will see in the next paper that this is possible, and they're doing it, and a follow-up. We've seen some tricks for like the layer-wise pre-training of the deep autoencoder. And we've seen an interesting hybrid structure on the decoder network where they've combined the LSTM with the 1D convolution which in this case works because those two parts of the network are trained together. So the LSTM knows what the 1D convolution will do with its output during the part where they're training the sequence-to-sequence model. So there's a question from Eduardo regarding considering the sensitivity to initial conditions. I wonder if the emulator will also show a similar behavior. For instance, the Lyapunov exponents are similar. So that this sensitivity could also be analyzed with simulations with the emulator. That is true. As the authors state, I think repeatedly, both in the introduction and in the conclusion, to them this is just the first step. This is just very, very roughly showing if it's possible at all, and then showing some, I guess, pretty pictures and some verification, mostly from the machine learning side of things, in terms of quantifying the results in terms of a bunch of, as we've seen, a bunch of error graphs. Here, yeah, I guess it would be interesting to more thoroughly compare not only whether the output itself behaves pleasingly, but also in robustly comparing whether the emulator, if I pick up, if we pick up the term again, actually behaves like the numerical solver, which ultimately, at least under some interpretation of this work, is what you would want, right? Yeah. I agree. Okay, I'm quickly gonna switch to the direct follow-up paper if anybody else has a question, or if Eduardo doesn't feel that I answered it sufficiently, which quite openly I probably didn't. And then I would just quickly switch papers. So this is a direct follow-up that I will try to be quick about. So this came out, I think 2 years after the original paper. With just 1 year, if you look at the year that they graph from the citation. It's a work that's really a direct follow-up. It's heavily self-citing. There's a short list of major changes and improvements. The very first one isn't even on any of these graphs. It's the fact that now they're training everything end to end. So the autoencoder is aware of the fact that its latent state representations, again called C in this case, so yeah, they mostly kept the notation. So X at a certain time point, t equals 0, goes to an encoder, and then is in a latent representation stage. And then there's a prediction model that takes this state and takes also other states, and then it goes back through the decoder, and then it's supposed to be an estimate of a future state of the input, right? So they have these encoder and these predictor and these decoder parts, and now they're training them all end to end. And there's this very nice figure, I think, that albeit not very robustly quantified, just visually shows very nicely what this means. So these are the principal components of the latent space. And then they project everything into a latent space, which is already lower dimensional, and then they run a principal component analysis on this. This time limiting just to 3, such that they can actually show these. So every point in this, across all the different colors, is a single input frame. All the points of the same input frame, all the points of the same simulation, so multiple input frames for the same simulation setup, have the same color. What you can see left to right, and especially nicely on the right, is that consecutive points from the same simulation, so the same movie, that are projected into the latent space through the encoder network, they very smoothly follow each other in latent space. Well, at least projected onto the first 3 principal components, right? So what that means is that the encoder tries to keep points that are close together temporally close together in latent space. One way to do this, something we saw before on the blog post, may just be that it keeps images or volumetric images that are similar, that for these it projects it onto latent space that are similar. And just because subsequent data frames from a video are similar, that might already do the trick. But it might also be a part of what comes out if you just jointly train this with the LSTM, such that the LSTM has a much simpler time of, if you will, just connecting the dots along the trajectory to get an idea where it is going, which is way easier on the right hand side, where you see way smoother trajectories than is on the left hand side, right? Essentially, the LSTM's job is to, from a short sequence of this, predict the next point. If you take a sequence of a certain length, because these points are so spread out, it's way harder to predict what's going to happen than in a case where everything's behaving much nicer and much smoother. Okay, this was a bit too long on the first point, what it means to train everything end to end. Even though it can be difficult to do in practice, on the original paper they trained the encoder and the sequence-to-sequence model with completely different methods of gradient descent. I think one was with the Adam method and the other one was with RMS prop, which are just 2 different things. And finding a training regimen that trains all the parameters of all the model parts at the same time can be a lot of pain for the first author that has to code this up. They even have, I think, some part on hyperparameter tuning somewhere later in the paper. The second big change relative to previously is here. They actually, let's actually grab this equation. I think this is getting what we want. They now have both the velocity and the density parts as inputs and outputs to the network, where in the previous paper they split between, they differed whether or not they either encode and decode the velocities or the pressure. So that's the second big part. One nice thing that, depending on where you want these things to go, can either be a step forward or a step backward, is that they are actively incorporating parts of that are also important in a numerical solver into this. So for the density information of these volumetric images, the network encodes subsequent input images into the latent state C. So C is already what has gone through the encoder. Then you have the predictor, which takes several of these and predicts the current or future state. Then you have the decoder, which takes this hidden state and produces, as I said, both velocity and density information. But then instead of, for the next state, passing both of these things unchanged back into the encoder network, what happens is this intermediate step where advection is done with a process that's informed explicitly by physics of fluid dynamics. So this advection step is incorporated as something really, really not machine learning into this machine learning algorithm, because they say it's comparatively cheap and it really, really helps. So there is no fear of combining these things where it helps, which I personally find very nice. From the perspective of having to replace everything with a neural network, of course, that might feel like a setback. I guess it depends on your point of view there. So that's the second thing. So they predict both velocity and pressure, and they re-eject part of that information into the network after passing through a physics step. And then the third part, which also got the paper its title, I think I already it's called way beyond that, I'm sorry for last one, is that they split up the latent state into different parts. So this is something I rambled on before a bit already, that one of the big topics about these autoencoders in the literature from the past few years has been trying to make sense of what the latent state does, finding out certain dimensions that correspond to certain things. And here they try to split this latent state into three different parts, one for the velocity, one for the density, and one for something that they call, I think, supervised, SP. And then they treat these differently. So first of all, there is the loss now that tries to keep the information within these individual parts to these individual parts. It's not a hard constraint, it's more like the soft constraint that we saw in the soft constraint type autoencoders before. If I quickly go back here. So this is more this type of constraint on the hidden layer activation. In fact, you will see it's exactly this type of loss, which they're using there again. So here, this type of loss. So they're splitting up, and part of that they're actually turning into supervised learning. So an autoencoder is an unsupervised training method. So it takes your data X and it tries to reconstruct that. You usually don't have ground truth latent states. So one way of getting structure into the latent state, which is used here, is that certain parts of the simulation setup that you want to be explicitly encoded in certain dimension of the latent space, you can just enforce this through a regression loss. So the overall loss still has these parts, which is the direct reconstruction and the reconstruction of future states. Now it has also the split loss parts that try to enforce the splitting of the latent state. But it has these supervised terms here, where for each simulation you know certain high-level setups, like is there a sink for smoke in one of the smoke simulations. We will see that in a figure. If you can control this, then one game you can control how this is encoded. Then one game you can play is you can encode a scene, and you can swap out the supervised parameters that you know the values for from another scene, and then you can decode that, and then you have changed something high-level semantic about the decoded image that you are producing. So there is this here, I think. Is this the nicest one? I think this one, yeah. So here's the ground truth evolution, and then there's an additional inflow. Let's see if we actually find that. I think it's probably this one. There's an additional inflow that is put that is not known during training, that is relevant for the prediction. And if you just predict that with the original image, of course, the network isn't going to catch up with that. But if you change the supervised parameters of the latent state, then you can change the whole scene that you're trying to decode at a high level like this, and you can influence the outcome in a very targeted fashion. Thinking if it makes sense to do the comparison again, if you trained an autoencoder in faces, you could try to, for every face you could know the age, and then you could have a single dimension of your latent space that you want to represent the age. You could train that to be the age of the person, and then when you encode a person, then you could use the full encoded vector for the face of that person, the picture of the face of the person, and then you could just change the age, and then you could decode again. I think that's how some of these image filters that came up in recent years work. And here the same thing with the same idea with some of the high-level parameters of the simulations, which is pretty cool. So these were the main things about this paper. To really see the improvements side by side, I guess I'm encouraging everyone to have a look at the images, at the videos. So I would ask the chat now, in the interest of time, because we're closing in on 1.5 hours. Is there a particular interest in us discussing anything about the third paper? That is D-fluids, which is more focusing on the decoder part and this idea of manipulating certain dimensions of the latent space. If there is any interest about any details, I'm happily discussing. Otherwise, I would skip this in the interest of time. And I would point out that in our original email for this one, the author has actually made a pretty nice. They made this for all of the publications. They have pretty nice images, pretty nice videos generated for this. But this actually is the only one, at least the sound works for me out of the 3 papers. Since there doesn't seem to be particular interest so far in the chat, I would just point you at the video for this. I know it's somewhat lazy, but this paper is something like an intermediate step between the main paper of today and then the latent space subdivisions that I just went through. If there is no other questions, I would kind of conclude today's session, at least the main content part. From my side, it was rather interesting to look at people having already looked into essentially training emulators for Navier-Stokes described systems. What kind of architectures they used in this particular setup. As we said in the beginning, it's much more small scale than what the nerve science we're usually dealing with, what they're trying to emulate here. There are clearly some limitations, and as Eduardo pointed out, there's a lot of evaluation to be done. So that might be something to either wait for future publications or to just get our hands on ourselves and just try it out. One thing that I found a bit odd about our main paper is the time comparison of the deep learning algorithm that runs optimized on a GPU versus the numerical solver that runs It runs on the CPU. A fairly quick search, again on YouTube, sorry for the video spam. A very quick search online. Yeah, this is a 2017 paper, just a title here. Large fluid simulations on a graphics card. Shows that there's also work on just speeding up the numerical solvers with the same underlying techniques that have made deep learning such a success, just hardware acceleration and smart ways of going about things, of putting stuff on the GPU. So I like the expertise to really judge whether this in comparison is entirely fair. Regarding fluid simulations, for those of you that find this particular topic particularly interesting, I'm already showing you the channel. So there is this YouTube channel. Now that I'm a YouTuber, I get to do shout outs, I guess, to other people's channels. It's something I like to watch once in a while. So what he does is he's a machine learning, or let's say, as sometimes we self-identify these days, an AI researcher that has a strong emphasis on rendering of fluids, actually. So the whole thing, the channel is called 2 Minute Papers. And he has a playlist on just simulating fluid, cloth, hair, and all the cool advances that he highlighted, I think just in the last 2 or 3 years. And as you see, this is much more condensed information than what you're getting here from our seminar. So if you're particularly interested in the in advances in the simulation of fluids with a strong emphasis on advances in machine learning and AI, I can really recommend that. Yeah. So that would be it from my side. If there's any more questions, I'm happy to answer them. Otherwise, I would stop the YouTube stream and then we can still chat in the Zoom afterwards. Okay, so in that case, I would conclude. The next session will probably be again in 2 weeks. Otherwise, we will update you soon enough, and then David will probably be joining us again. Otherwise, thanks for the participation, thanks for the questions, and thanks for your attention.